Hi guys, this is your first notes video for the spring semester of 2015. Here is your general outline of where we're going. Today we are talking about radiation. We're then going to go into telescopes, and then we're going to talk about different observatories. We'll be moving into different types of astronomies, different types of instruments, and non-electromagnetic astronomy only briefly. At the conclusion of this unit, you will be working on the projects that you began where you chose a topic that could be addressed by some form of astronomy. You chose a problem as a table. That is going to be your project for this unit. We're going to develop that more probably beginning next week and more the following week, where you guys will be taking that problem and finding an astronomical object or observatory that will be addressing that problem. So we know that light is a wave, and it's classified as a wave because it can be physically measured. So the two ways that we measure waves are in terms of wavelength and frequency. And the symbols that we use are the lambda symbol for wavelength and an F for frequency. And they're inversely proportional. So as we have a wave, which is measured from the entire passage of the wave, so either crest to crest or trough to trough, that would be an entire wave. And then the frequency is how many units happen in a given period of time. So if we were to take just this period of the wave, we can see that there are 1, 2, 3, 4 waves. That's the frequency. So it would have a frequency of 4F. But then the wavelength would be the actual physical measurement of the length of the wave. And we can see that they're inversely proportional. And in this equation, C is always equal to the speed of light. So if your frequency is inversely proportional to your wavelength, you would just take your wavelength, your speed of light and divide it by your wavelength. You don't really need to know that, but what you would need to know is that they are inversely proportional. In this program, it changed the symbol for wavelength to an L. It's not recognizing the Greek letter, but it is a lambda. So we know that wavelengths of light are measured in physical units. And light is more than just visible light. So the EM spectrum encompasses everything from radio waves to gamma rays. So the ways that we measure them are in nanometers and in angstroms. So that is the symbol for an angstrom and the symbol for a nanometer. But in terms of radio waves, we can actually measure them in physical meters because they can be as long as a football field and as tall as a building. So the size of the wave determines what size of telescope we would need in order to detect it, and also where we would put that telescope, whether it could be ground-based or has to be space-based. So 1 nanometer, just to give you the context, is 10 to the negative 9th, that should be negative 9, exponent negative 9 meters. So this is incredibly small. And an angstrom is even smaller than that. So it is a 10th of a nanometer. So just for the context, visible light has this specific range from 400 to 700 nanometers. So visible light is a specific section of the EM spectrum, and it's delineated from other portions of the EM spectrum by that specific wavelength. So every color has its own specific wavelength. So from the color spectrum activity that you guys did, you saw that your UV, which is over here, is a shorter wavelength than your infrared, which is a much longer wavelength. So if you look at just when you're in the classroom looking at your models around the room, your infrared was like 1,000 and your UV was 30. So that means our red is a longer wavelength than our violet. But our violet is a higher frequency because remember they're inversely proportional. So our red would be a long wavelength and it would be progressively getting shorter. So our gamma ray, this is our section of short wavelength, high frequency. Our radio is our section of long wavelength, low frequency. So here we can see the prism that is splitting up each of the components of white light into each of the colors of the spectrum. This is what a rainbow does as well. So the water droplets in the atmosphere act as a prism and change the speed of light into each of their component colors. So that's how we're able to see the Roy G. Biv spectrum. So we can see the ultraviolet would be over to the left. Where's my cursor? Our ultraviolet would be over to the left over here, and our infrared would be over here. So, and just like in your lab, the Herschel's lab we just did, we can measure infrared because even though we cannot see it, we can still detect a temperature in that portion of the spectrum. And you guys just did that. So Pink Floyd kind of had the right idea with their album cover. We can see white light that is entering into the prism. This is supposed to be a prism. And exiting, you have the rainbow. So one color goes in, multiple colors come out because the prism is actually splitting up and refracting each of the components of light. And if you look very closely, this is one of their album covers. These are two different versions of the Dark Side of the Moon. This is the original Dark Side of the Moon album cover. And if you look, you can actually see in the components of the rainbow, you can see absorption spectra. So you can see these tiny little black lines. So I've heard that this is the spectra of the sun, but I checked it out. Not quite. I think it's helium. So the different wavelengths and frequency have an influence on where we put those telescopes to observe, because we have gamma ray astronomy, we have X-ray astronomy, we have radio wave astronomy, we have UV astronomy and infrared. But we only have specific atmospheric windows. So we can see that we've got an atmospheric window right here that corresponds with the visual. So hence we can see visible colors on our surface. So that's one atmospheric window. Our second atmospheric window, and the largest, is our radio waves. So these two telescopes can be put on the ground. So we can have visual observing telescopes and we can have radio telescopes on the ground. All of these other wavelengths, so gamma rays, X-rays, UV, we need satellites to observe. So you can see that infrared has a kind of funky atmospheric window, and that some can be done from the ground, some can be done from right about here, and others, so you have your near infrared and your far infrared, they have to be done from space. So here's another picture showing telescopes in the atmosphere. So we can see orbiting telescopes for gamma rays, X-rays, and UV. We can see ground-based telescopes for visible light. We can see this funky atmospheric window for infrared. Most infrared is done from space. We can see ground-based radio observatories. Notice that this telescope and this telescope look vastly different. This is a typical observing telescopic tube. This looks more like a radio dish or a satellite dish. That's because radio waves are so big. You have to have a big dish that can actually pick up those waves. So the largest radio telescope, as we'll see later on in this unit, is located in a cave in, totally drawing a blank, I believe it's Costa Rica. It's called the Atacama Observatory, and it's nearly a half a mile across. They literally just paved in this limestone cave and made it a radio telescope. So here again, we can actually see the portions of the spectra and pictures of the specific satellites that observe. You can see we got a plane right here. This is called SOFIA. That is the Stratospheric Observing Flying Infrared Airplane, I believe. I should know that. Here we can see the radio window is much bigger. Visible is actually the smallest portion of the spectra, but this is where we have all of our ground-based observing that is done. So SOFIA is taking advantage of this narrow atmospheric window right here. So this is a gutted 747 plane that they've put a telescope in. And I'll talk more about SOFIA in just a moment. So I just wanted to give you guys a very brief history of the space age. So most people would say that the space age really started in the late 50s with the formation of NASA. But really it started around World War II because the Germans invented the first rockets. Well, then you had, the Holocaust and Hitler and Nazis. And Hitler saw that all of these people that were making rockets, that they had the potential for weapons. Well, he wanted to use them, but he didn't want anyone else to use them. So most of those scientists were either contracted by the Nazis or they escaped to other countries. So they went to either the US or the Soviets. So we wanted to get all of the good scientists, so such as Wernher von Braun, who was actually the founder of JPL. He was a very young rocket scientist. He actually designed most of the bombs that the Nazi Germans used, and he was Hitler's kind of right-hand man. But then we got him, and the reason we got him, the Brits wanted him, but the Brits wanted to extradite and execute him, but we instead got him, and he became this huge hero. But really, he designed all of the bombs that did all of the damage in the UK. So then in the late 50s, we had the formation of NASA. We had the development of Project Gemini, which paved the way for Apollo. So Gemini, the first Gemini astronauts were testing out the feasibility of actually sending human beings to space. Before that, they sent monkeys. Before that, they sent rats. There are many, many monkeys that went to space and a couple dogs. So Gemini, it was what had to happen to just prove that humans wouldn't die when they actually left Earth's gravity. In the 60s, we had the Cold War, which we won, and we won this really in space. There was no one that actually physically died in the Cold War, as you should know, but because we were the first to send a man to moon in the Apollo missions, we technically won. So we had the first man on the moon in 1969, last man on the moon in 1972. There was a very narrow window there. No one has been to the moon since. In the 70s, we had the focus really on the science, not so much the exploration. So we had this age of the great observatories. We had the age of planetary science. In the 80s, we really kind of thwarted the science because in the 60s, we said, well, we went to the moon, let's go on to Mars. And that was supposed to happen in the 70s, and it didn't. And it was supposed to happen in the 80s, but instead they came up with a shuttle, which was basically just a plane that would put satellites in space. So the shuttle stayed about 4 times lower than Apollo ever went. So it was basically in low Earth orbit, which is where science has been for the most part ever since. So there was very little science. This was mainly the age of communications, satellites. So this is when we had our first satellite TV, satellite telephones. That was all in this age, thanks to the shuttle, but very little science was done. So with that background, here are our great observatories. So these took a long time to build, starting in the 70s. So we have the Gamma Ray Observatory. We have Chandra, that's the Compton Gamma Ray Observatory, not like Compton, downtown LA, named after some famous scientist. Chandra, named after a guy who was from India with a very long last name that Chandra sounds much better than. That is the X-ray Observatory. That is the Crab Pulsar that took a picture of an X-ray. Hubble Space Telescope, and then Spitzer, which is an infrared array that we will hopefully get to speak to the commander of that mission like we did last year when we went to JPL. It was pretty amazing. So here's showing the wavelengths of each of those. So gamma ray, X-ray, UV. Hubble takes images in both visible, UV, and infrared. And then we have our Spitzer, which is just infrared. I wanted to talk real briefly about SOFIA because this is launched from Armstrong, which used to be, I can't even remember the name of it, the base that is out in the Mojave. So this is a stratospheric observatory. So they took this gutted 747 and they put this telescope in the side. And the cool thing about this is this does these 12-hour flights at night, and it has the widest range, even though it's in the infrared. This has a wider range of wavelengths because they're observing over a bigger portion of the spectrum than just infrared than any other telescope out there. So this is providing a ton of science. And the reason I'm even bringing this up is because I applied to be a teacher ambassador on the urging of my students from last year, and I should find out in about 3 weeks whether I get to fly on that plane. So here again is just an overview of the EM spectrum and astronomy, showing you where each of those astronomies are done and some samples of what those telescopes look like. So there's cute little SOFIA way down here. There would be Spitzer. There's your Hubble. So that is where we are going to stop. Have a wonderful weekend.